Thank you, Francisco. Yeah, I'm excited to share this work with everyone. This was a collaboration with Tito Aravello, Chinmay Garg, Winnie Kwong, Francisco Yanda, and David Wettergreen, George Cantor. The authors are at the Robotics Institute at Carnegie Mellon and the Federico Santa Maria Technical University.
It's the left and right arrow on the clicker.
Yeah, it's there you go. Okay, so the high-level motivation, as many of you may know, forest fires are becoming increasingly prevalent and dangerous and deadly worldwide. This is driven by a number of factors, including poor forest management, increasing urban woodland interface, and the pressures of climate change. And to mitigate or fight these forest fires, we have a lack of manpower, so this kind of motivates robotic solutions, especially because this work can be strenuous, dirty, and dangerous. So in this work, we propose a UAV mapping system that maps out an area to inform an unmanned ground vehicle that can go in and actually remove fuel. And this is to mitigate the risk of forest fires. So specifically, the UAV provides a two-layer map. One represents the areas that the UAV can and cannot traverse, and the other represents the fuel that we need to remove. So there's many different types of fuel in forest fires. In this work, we're specifically looking at live vegetation that can be removed by a mulching attachment on this UGV. So we have a modular multi-sensor payload. This has a Velodyne LiDAR, an IMU, and a stereo pair of cameras. There's a power supply board that draws power from the battery on the UAV. There's a Teensy microcontroller that provides pulse per second synchronization, and an onboard consumer-grade computer with an i7 processor. If you look at our system architecture, you can see that there are three primary sensing modalities. That's the IMU, LiDAR, and camera. GPS is notably absent. This is because the quality of GPS data can be severely degraded under the canopy. If you look at the top kind of flow, all of these sensing modalities are fed into our simultaneous localization and mapping system. This builds a map of the environment and lets the UAV know where it is within this map. After a mission is complete, we get a dense point cloud that represents all the registered LiDAR scans, and this is sent to our geometric processing that determines the traversability and exported as a 2D traversability map. On the bottom, you can see that we have a camera, which goes to a semantic segmentation system. We take the semantic segmentation image, the LiDAR, and the 6DOF pose estimate from SLAM to build an online semantic 3D map that represents the fuel and the other classes in our environment. And then we downcast this into a 2D map and send this along with the traversability to inform the UGV path planning.
Press the center button.
Which one? The screen is black here.
Yeah.
Oh, okay.
Yikes. Okay. It is plugged in, that's power.
Yeah. So this is an overview of our simultaneous localization and mapping system. As I mentioned, we don't have GPS, so this is kind of critical for understanding the environment. This is a tightly coupled system inspired by two common SLAM systems, VilSLAM and LeoSLAM. LeoSLAM does not have a visual front end, so this can kind of be thought of as adding the visual modality to this. And we really wanted to have the ability to either run an IMU LiDAR and IMU stereo system, because in certain situations, one of these paired modalities might be stronger. This system is tightly coupled because, as you can see, there's a number of feedbacks between the modalities. For example, the LiDAR and the visual odometry are fed back as a prior into the pre-integration step for the LiDAR. Diving a bit more into the individual modalities, the visual front end matches orb features between the images in the stereo pair and then matches them frame to frame. And these provide a visual constraint in the factor graph. The IMU takes a number of measurements in time and pre-integrates them using a simple motion model. This leads to an IMU factor in the factor graph. And then the LiDAR, we take the most recent scan from the LiDAR And we use the IMU initialization to get a course registration, and then we further refine this registration with the global map using ICP. Here we can also include a GPS factor if GPS is present, and LiDAR loop closure factors if those are detected. When we ran this in 2 trials in a forest environment, we found that we got fairly good accuracy. In both cases, we found that the LiDAR odometry was more reliable than the visual-based one. We saw a lot of issues if you got motion blur, that the visual odometry would be severely degraded. Yeah, and this is relative to a GPS baseline, which we had in this situation because the canopy was open. Moving on to semantics. So we chose to do semantics in the image domain. We segmented out 4 classes. One is fuel, which I mentioned is low vegetation that we can remove. We also have the canopies and the trunks of the trees, and a background class that represents everything else. In practice, this is dirt, roads, and sky. We chose to use the segformer architecture for semantic segmentation. This is a state-of-the-art deep learning-based approach, and we chose it because it demonstrates really strong robustness to domain shift, which we thought would be useful given the limited training data. So we had 2 different data sets. One was a manually labeled set of data, about 150 images taken from one forest site. As you can see on the bottom, there's some really fine detail that's extremely hard to label precisely, but overall, this data set is quite accurately labeled. We also had a 4,000 image data set taken from simulation. So there's a procedurally generated forest environment, and we our collaborators rendered out photorealistic images from this data and associated pixel perfect ground truth. So this is really useful because the data set is larger and the labels are more accurate. So we tried a number of experiments. The first one is we trained a model just using all of our synthetic data, and we applied it to the real world data. So that's this dot on the left. We got about 0.35 mean intersection over union. This isn't great. We tried experiments where we added increasing sized training sets from the real data and tested over 5 folds on the real data. And we found that performance kind of increased a little bit, but didn't really reach a particularly high level. Then we simply removed the synthetic data from the experiment and took our cityscapes pre-trained model and trained on increasing sized sets of real images and tested on the held out test set. I found that this actually did much better. And surprisingly, the performance between 30 images and 120 is somewhat constant. So I think there's a bit of a caveat that all of these images were taken from the same geographic area. So they are very, very similar to each other, but this is somewhat surprising that so few images yield such good results. If we look a little bit more into the evaluation, again, this is trained on a set of this real data and tested on the test set across 5 folds of the data set. We get pretty good performance. There's kind of expected confusions between trunks and canopies as they overlap a fair bit, and also between canopies and fuel, since these look pretty similar. On the right, you can see examples on our unlabeled test set, which is geographically distinct from the training data. The results seem pretty good. I would just like to point out that it is pretty visually ambiguous to tell the difference between fuel and canopy. So this is something that even we struggled with. So there are maybe places where the network made mistakes here, but it is quite a hard problem. And it did it again. Okay, so now that we have semantic understanding in the 2D image, we want to move this into a 3D representation. So we took a publicly available RGBD semantic semantic mapping framework and modified it to work with LiDAR. Basically, we take the image, we pass it through a semantic segmentation network. We use the calibrated fixed intrinsics and extrinsics between the LiDAR and the camera. And we use this to texture the point cloud with semantics. So for every point within the field of view, we project it into the image plane and associate the class confidences for each class with that point. Now we use the 6DOF pose estimate from the SLAM system to transform the semantic point cloud into the world coordinate frame. And then we update a semantic map. It's an octamap that has semantic information. So this represents the occupancy in a probabilistic manner. And we also update the semantics for each voxel using either a max confidence fusion approach or a Bayesian fusion approach. And then we export the locations and class per voxel for this map.
You're pressing the wrong one.
Oh, I'm sorry. Okay, that makes sense.
Yes.
Sorry, I apologize for this. So here you can see an example of our semantic mapping in action. So we have this UAV pose moving around the scene, and it's continuing to build up this voxelized semantic representation of the world. So you can see these green representing the trunks, purple representing the canopy, red representing fuel, and black representing the background. And everything else you see is the map of the world generated by the SLAM system. So one thing to point out is we're actually covering a pretty small region of this map with our camera viewpoint. So this is one thing to note, that because we're doing semantic segmentation in the image space, that's one limitation. But in general, it seems like even though we're not considering geometry in our semantic mapping, it's doing pretty well. So our trunks are well localized, our canopies appear above the ground, and our fuel is on the ground.
That's the right arrow.
Okay, so moving into our traversability analysis, as I mentioned before, we do this based on a point cloud computed from the entire trajectory. We begin by segmenting out the ground from the non-ground points. This is done with cloth simulation filtering, which is a very common approach for doing this in the airborne LiDAR literature. We have a simple heuristic approach for traversability, which is simply taking the ratio of ground to non-ground points and thresholding them. But this is over grid cells taken over the 2D region. But this is fairly simplistic and doesn't actually consider features of the terrain. So we moved on to a more sophisticated approach that considers both the roughness of the terrain and the slope. And we needed some method for fusing these two metrics. So as a first approach, we tried a fuzzy logic-based approach. So these metrics are encoded in fuzzy sets using these membership functions. So for the slope, we have smooth, rough, and rocky, or sorry, the roughness rather, we have smooth, rough, and rocky, and the slope we have flat, sloped, and steep. So numeric contribution contributes some amount to each of these sets. And this approach is inspired by the work of Howard et al. About 2 decades ago. And then we use handcrafted rules to combine these two sets. So for example, if the slope is flat and the terrain is smooth, our traversability is high. Whereas if the slope is steep and the roughness is rocky, our traversability is low. And then we get back a numeric value using the centroid method and these output membership functions. This is all kind of traditional fuzzy logic approaches in this domain. So this gets us a result that seems to respect the terrain a little better than our heuristic function, which is pretty noisy. One thing to note is it's really hard to figure out how well we're doing because we don't have a data set representing ground truth traversability. So this is our best guess at what works well, and it seems to represent, for example, you can see there's two kind of smooth regions and a path that show up pretty well in the fuzzy traversability result. So in conclusion, we present a SLAM system, a semantic mapping system, and a traversability analysis system. In the forestry domain, to the best of our knowledge, we are the first approach to do all three of these in an integrated manner for a UAV. And this produces a 3D semantic map and a 2D traversability map. And we believe that these are useful sets of data to inform a UGV for these sort of vegetation clearing operations. So in the future, we'd like to incorporate the semantics into the traversability analysis, which is currently just using the geometric information from the scene. As opposed to doing the traversability analysis at the end of the mission, we'd like to make it online, or at least in batch. We'd like to continue doing real world deployments, and this is where we'll start to actually understand whether our system is working as we anticipate, and maybe start to build up some quantitative metrics that allow us to evaluate the quality of some of these subsystems. And then we'd like to explore active perception, so we can online begin spending more sensing effort on areas of the map that require further refinement. I'd like to thank Rui Nunch, Duda Andrada, Professor Paulo Peixoto, and Professor João-Felipe Vieira for providing training images. And then we received financial support from the Safe Forest Project and the Chilean National Institute of Science. Thank you for your attention. Are there any questions?
Well, thank you again for a great talk. Maybe the first one would be a comment that we've done experiments also with forest cementation, and we get the feeling that 100, 200 images is a good starting point.
Okay.
So don't be too surprised by that. One thing though we've noticed is when you do the plot, because often like in machine learning, there's power loss. It's like you double your data set, you gain 3%. So if you plot the stimulon, you tend to get a better feeling of how the curve goes. Which is scary because at one point, you realize that if you want to get 10% more, it's like you have to have like data set which is like 100 times bigger than what you have. So it's sort of like a battle you have to fight constantly. But at least you're better able to see it, because normally more data should translate in better performance. But that being said, so very interesting. And have you thought about trying to probe the ground with the robots, the ground robot, to actually get traversability ground truth? Because that's one big issue is right now. You develop handcrafted features and you hope that this will translate into traversability. But actually getting, when you talk about active precision, actually send your robot, the ground robot, to drive where you think it's drivable and see what's the response of the robot to see if it actually is traversable.
Yeah, so I think that makes a lot of sense. We actually don't have the UGV. This is our collaborators. So that definitely sounds like a good long-term goal. But yeah, there's a lot of integration issues for this project. But no, as a long-term goal, that definitely sounds very interesting.
Thank you very much.
Yeah.
For summer.
Yeah.
Thanks. So that was a really nice talk. I was wondering if you have been looking at, so a lot of fuels reduction programs focus on thinning projects. So where you're actually thinning trunks and not some like in the Western US, especially where there's just like millions of dollars going into fuels reduction now. So I'm wondering, this relates to the first talk in some way also, is that are you thinking about how you map the tree population and whether or not you can see the diameters of not only the understory, but the diameters of trees and those younger trees that may need to be removed for fuels reduction programs, because that would be incredibly helpful. Thanks.
Yeah, I think we're starting to think about that direction, and we'd like to see a much better coupling between our semantics and our 3D understanding. So it might be much easier to measure the diameter of a trunk in an individual scan, rather than the semantic map that builds up noise across the entire accumulation process. But yeah, that makes a lot of sense. So I can respond to that question in chat. Yeah, so the reason we chose to use Octomaps is because it is really well suited to online implementation. So it's actually a pretty well optimized framework that's specifically meant for online probabilistic map updates.
So you talked a bit about wanting to do more of this computation online in the future. I was wondering, what do you think are the fundamental computational barriers stopping you? What are the hard parts of the compute right now?
So this wasn't my part of the work, so I can't really speak to that well, but I think there's no fundamental barriers to it. It's just finding an optimized map representation and actually implementing it. So I think it'd be nice if we could leverage something like the semantic Octomap that we have, so we can accumulate observations using the same framework in an online manner. And then because all the traversability work we've done has been done independently on different voxels. So if you don't have to regrid your world, that would be a performance boost.
Thank you.
Maybe a quick question about the LiDAR odometry. So as far as I understood, those were lone variants.
Yes.
You were using, right? Did you have any issues with the features in the forest? Because loans, these line and plane features were designed for urban environments initially.
So again, this wasn't my part of the work, so I didn't dig too much into it, but it seemed like the LiDAR was relatively robust. And then maybe Francisco can comment on this, but it seemed like there were some catastrophic failures, but in general, it was pretty good.
Yeah, sometimes when the GPS was good enough, the LiDAR odometry had a boost in performance. But in general, the long part plus the IMU did really well in the